Welcome to this ELEEP Virtual Discussion with David Fried on net power. My name is Andreas Graf, and I'm a researcher on climate and energy policy at Ecologic Institute in Berlin. For those who do not know ELEEP, ELEEP stands for Emerging Leaders in Environmental and Energy Policy Network and is a dynamic membership-only forum for early and mid-career North American and European leaders working on environmental and energy issues. Members debate topics of the day online, meet regularly for face-to-face activities such as study tours, and collaborate on transatlantic impact projects. It's a joint project of Ecologic Institute in Berlin, in the US, and the Atlantic Council. This discussion today is part of the Transatlantic Energy and Climate Dialogue, a grant made possible by the European Union, the Robert Bosch Foundation, and the Allianz Foundation for North America. And to find out more about the network, visit our website at www.eleep.eu. And today, we're here to talk about CCS. And as those viewers will most likely know, CCS stands for carbon capture and sequestration, or storage, and refers to the process of capturing CO2 from power generation or an industrial process and preventing its release in the atmosphere. For many, CCS is a critical part of long-term decarbonization, arguing that the costs of energy transition increase substantially without CCS, and it may be the only technology to reduce certain types of emissions in the industrial sector. Today, we're here to talk about one CCS technology, net power, and with us today to talk about this technology is David Fried and Damien Beauchamp, two principals from 8 Rivers Capital, a technology commercialization firm based in North Carolina. And I'll hand off now to you to introduce what you do at 8 Rivers Capital and to tell us a little bit about net power.
So I'm Damien Beauchamp, principal at 8 Rivers Networks, 8 Rivers Capital. I work on business development for net power. I also look at CO2 utilization processes and conversion processes for sequestration. And I also work on various hydrogen generation platforms that we look to exploit in the future.
Thanks, Damien. Thanks, Andreas. My name is David Fried. I've been with 8 Rivers now for about, since the beginning, really, of net power, almost 6.5 years. My background is in engineering. I serve as the project manager for 8 Rivers on the net power demonstration facility that I'll talk about in a little bit. So because we only have a little bit of time here, I'll move rather quickly through some slides, and then if we have any questions at the end, we can do those if we need to. Please always feel free to reach out to us at info@netpower.com for more information. So next slide, please. So the World Economic Forum really wants to, Steve Bowles and Ignacio Galán, who are the chairs of the Future Electricity, look at investing in no-regret areas that have a positive business case and will be palatable in any economic climate. We always start with net power at economics because in energy we feel economics drives technology selection and technology deployment more than really anything else. So our real goal here is to make our technology competitive in exactly this way that is palatable in any economic climate globally, with or without carbon regulation, and using the technology that we have today. So if we go next slide. So what is net power? So net power is a technology that was invented about 8 years ago by a combination of people here at 8 Rivers Capital. 8 Rivers is, as Andreas mentioned, a technology development firm based in Durham, North Carolina. We come up with initial industrial scale technologies and then partner with large corporations in order to deploy those technologies to market. This technology, the net power technology, is a partnership between ourselves, CB&I, Exelon, and Toshiba. It's based on what we call the alum cycle, after the head inventor Rodney Alum, whose background was in large industrial processes and integration, formerly at Air Products and Chemicals. Historically, people always think about CCS as a cost-prohibitive technology, and we think that's because it's historically been based on post-combustion captures or traditional oxy-combustion systems. So traditional air combustion, you start with nitrogen, oxygen, and natural gas. In the case of natural gas here, we'll talk predominantly about natural gas because that's where the alum cycle is really starting on. There's other applications that we can talk about in the future, but for now we're focused on natural gas. So traditional air combustion requires, you don't separate the oxygen from the nitrogen, you burn, that creates some NOx. It also dilutes the CO2 in the flue gas, so that predominantly what your flue gas is nitrogen. And what we've tried to develop what industry has tried to develop over the past several years is amine post-combustion or other post-combustion solvents that go and grab that CO2 away from the nitrogen, and then you have to heat up that solvent in order to release the CO2, which then can be compressed and put into a pipeline. That's what you think about with traditional post-combustion CCS technologies. There's a second wave of technologies that are non-amine based, but in general, it's really around grabbing the CO2 in existing flue gas, heating it up in order to remove that CO2, and then compressing and putting it out into a pipeline. Oxy-combustion technologies are ones where you remove the nitrogen before you go into your combustion process. That enables you to not have NOx, but it also enables you to not have to separate the CO2 from the nitrogen. All you have to do is drop out the water, and then you have a low pressure, traditionally, stream of near pure CO2, which you can then put into a pipeline and sequester or use in industrial sources. The alum cycle is a variant of traditional oxy-combustion systems with a few exceptions. So traditional oxy-combustion systems, they utilize a steam cycle by which to transfer the power, which is known as a traditional Rankine cycle. We instead utilize what's known as a Brayton cycle, which is effectively what's a gas turbine cycle. The difference is instead of just releasing the heat up the atmosphere that would come out of the back of a traditional Brayton cycle, in a combined cycle plant, what they're doing is they boil water with the heat that comes out the back of a gas turbine. We instead utilize carbon dioxide as the recirculation fluid within our system. And you can see over here on the right on the graph, really the width of the lines here is the amount of mass going through the system. So you've got oxygen and natural gas coming in. That's traditional oxy-combustion, right? And then that comes in your combustor and your turbine. You come out of that turbine and you go into what's called a recuperative heat exchanger. So that heat exchanger is going to drop the temperature coming out of that turbine down to near ambient conditions. Once you get down to near ambient conditions, you can remove the water in liquid form. That can go to your cooling towers or it can go elsewhere, but it's effectively a pure stream of liquid water. You then are going to recirculate most of that CO2 back through the heat exchanger into the combustion turbine. So you can see here what's mostly going around our system is CO2, not water in traditional power plants. What the benefit of this is that I'm already paying for the compression and pumping within my system in order for my cycle to work. So the additional work in order to produce the CO2 for pipeline, the CO2 is, as we say, pipeline ready in both quality and pressure. So we can send that out into the market without having to do additional work. That's very different from traditional CCS, where in the air version you have to both remove it from the flue gas using an amine post-combustion system or other post-combustion systems, or an oxy-combustion where you're using a steam cycle and you have to pressurize the CO2 because it's coming out at near atmospheric or below atmospheric. So that's what this technology is based on. If you go next slide, please. What unlocks this technology is every piece of equipment in the plant is commercially available today with the exception of the turbine. And we've partnered with a great organization in Toshiba that enables us to leverage a lot of their existing expertise. This technology really looks like a gas turbine coupled with steam turbine technology. So gas turbine technologies typically are higher temperature, 1300 to 1600 C, J-class or even higher than that. The problem is that we're at higher pressure and with a working fluid of carbon dioxide, which is not traditional gas turbine technology. Steam turbine technology is typically high pressure, 24 to 31 megapascals, but it's lower temperature, 600 to 750 C. Again, we're higher temperature and our working fluid is CO2. So we're using a combination of a marriage of steam and gas turbine technology so that we can apply the engineering to this new product that Toshiba will be delivering to the market, coupled with the alum cycle. The combustor for us was really the only new piece of technology, and that's why, in partnership with Toshiba, Toshiba did a lot of great work in testing out a 300 bar combustor, which we tested back in 2011, 2012, and 2013. That gave us the confidence to now move on to our demonstration facility. You go next slide, please. So for the demonstration facility, we're building a 50 megawatt thermal natural gas demonstration plant for a traditional power plant that would produce enough power for about 15,000 homes. That plant is scaled down from a commercial version, which is about 500 megawatts thermal. The site is in LaPorte, Texas, which is southeast of Houston along the Houston Gulf Ship Channel. It'll include all core components of the alum cycle, and we'll take it from startup to shutdown and all the other modes of operation that we need in order to prove that this cycle has the robustness of a commercial facility. We'll pull an oxygen from a dedicated ASU that's next door, and that project, as we said, is fully funded, includes all construction engineering and testing and commercial development activities. You can see over here on the top picture was what the plant will look like, although it's Texas, probably a little less green. And then bottom is where the site picture was taken about 2 weeks ago down in Texas. So we continue to make a lot of progress. We will begin commissioning. I'll show schedule a little bit, but we'll begin commissioning later this year. Next slide, please. So really, as we say, the demonstration plant is a step for us onto the commercial. We really only feel this technology can have the kind of impact we need as the demonstration plant is successful and gets us to that first commercial plant and beyond. And the reason people are so excited about this technology is not just that it's an interesting CCS technology, and I'll talk about a little bit about the importance of CCS, but it's a CCS technology that is very applicable to today's electricity market and the future electricity market. So one of the things that people talk a lot about in the power markets is with the growth of renewables and the reduction of baseload power is the need for operational flexibility. And so in traditional power plants, your turn down is limited by your air permit. As you turn down a plant, carbon monoxide and NOx emissions increase, and so our plant, because we don't have NOx emissions, because we have no nitrogen that goes through our combustor, and CO doesn't degrade because we've got this huge recycle that buffers against any of that. Our turn down is not limited by air permits, so we can go down to near zero load on the grid, which to go from zero load to 295 megawatts, which is the electric output of our commercial facilities, is an incredibly fast responsiveness. It's something that's very important for grid operators and owners of these future facilities. We also have operational flexibility because we can store oxygen, because we are outputting carbon, and we can change around our controls within the plant. We effectively have a 30 megawatt or 40 megawatt swing that we can play with depending on what's happening in the power grid. So as power prices are going up, you're going to increase the amount of oxygen that you might take from the storage. As prices go down, you would increase the amount of oxygen that you produce for liquid markets or other things like that. Ramp rates we would expect to be comparable with where your best-in-class combined cycles are. For cold, it's going to be a little bit, based on where we currently are, no more than 3 to 4 hours. When it's warm or hot, we're going to be at 2 to 5% per minute. Sorry, can somebody mute their microphone, please? Give them some feedback. Thank you. There's a large amount of siting flexibility in places like the Western United States or China or India or the Middle East. Water is becoming an interesting, a more critical concern when it comes to siting power plants. Our plant enables us to go to zero water need. We're not a steam cycle, so we don't need water within the core process. And if we go air-cooled condensers, we get a slight efficiency reduction, 2 to 3%, but we don't need water. So that's very important for a lot of areas in the world that are increasingly undergoing water stress. We also can utilize alternative water sources, things like non-potable or brackish water, as a water source because we don't have this direct integration with the steam cycle that requires ultra-pure water or near very pure water. We can go in non-attainment zones because we're going to sequester carbon, because we don't have NOx concerns. Places like Los Angeles or Houston, where they're around the cities, are non-attainment zones where you can't put up new production that will output additional air emissions. The net power plant can go. One of the interesting parts about this technology is because it's a closed loop and the only input to the system is through an air separation unit, we really are not impacted by height, by by elevation. So in places like in Colorado or other places around wherever there's elevation, you're not going to have a reduction in efficiency and a reduction in output that you would see with a traditional combined cycle. We also talk about flexibility of sulfur, nitrogen, and other acid gases within the fuel gas that really don't impact us as much as a traditional plant. So from a high level perspective, this plant will output about 295 megawatts. We'll produce about 800,000 tons a year of CO2 at pipeline quality and pressure. We also, because we have an ASU, produce a lot of nitrogen, which can be used for industrial uses. The oxygen plant is about 3,500 tons a day, which is very in line with what's commercially available. And the footprint of the plant is about 13 acres, which is much smaller. You get smaller because you have a higher pressure system. And you can see a little picture of it, a rendering up on the top right. Go ahead, next slide, please. So here's where we are in terms of our development. We're in the middle now of 2016, and we're in the middle of we're finalizing, doing a lot of the final EPC work on the site. Our expectation is that we'll begin commissioning in the end of this year, and then start testing in the beginning of 2017. And that may continue through 2018, depending on what we need. Some customers only want to see a little bit of testing. Others want to see a lot more. We right now are out doing commercial development. We've already started on the commercial design of the plant. As you've seen some of the information from that effort, we continue to refine that effort. Our goal is to have a notice to proceed on the first commercial facility by the end of 2017. Next slide, please. So and this is a summary of the following slides, not looking backwards. In a world evolving towards cleaner energy, net power is what we feel is more relevant and required than ever. Total addressable market for new power is 1.5 terawatts of power. Our view is that renewables by themselves, and not only our view, we'll provide some other views as well, renewables by themselves won't enable us to get to the climate targets that people have set out without significant cost implications, subject to a huge disruptive technology coming in the market. Even so, net power provides really a technology that enables us to keep power prices low, maintain grid stability and flexibility, and to support a growing industrial load while meeting proposed climate targets. So there's a lot of big move from coal to gas right now. That's half carbon. Net power enables you to go to zero carbon on your baseload power and your dispatchable power. For us, where we'll start is enhanced oil recovery. It's a market that could support a lot of pipelines. In the U.S., enhanced oil recovery has produced about 5,600 miles of CO2 pipeline. That is economic, not based on any CCS regulation. That's based on enhanced oil recovery. So we'll tie into that network and continue to build it out. That'll provide really a framework for which to build out a CCS infrastructure. And what we consider net power to be a true no regrets option, where plants can be capture ready. EPA in the U.S. or other regulations internationally will produce costs at comparable rates. Goal is to produce electricity at comparable rates to combined cycle plants, but yet, just no matter what happens on NOx or CO2 emissions, people are ready for those if those emissions taxes ever come, we'll be ready for those. Next slide, please. So, we talk about electricity costs a lot when it comes to power. It's something that electricity costs has a huge implication on jobs and national GDP. There's some figures over here that on the right on what kind of impact a 10% increase in electricity prices would have out to 2040. It's a significant amount of job losses and a significant loss in national GDP. So we want to make a trade-off. We don't want to lose the benefits of renewables and zero carbon technologies, but we don't want to increase the price of power. So if you look at kind of what data looks like from several studies out there in the Electricity Journal, cost of electricity with about 173% renewable portfolio standard would increase by about 7 times to achieve that. If you go to half combined cycle and half RPS, it increases by almost double. We think with net power, we actually will be beneficial to the price of electricity. And if you still wanted to have a significant renewable portfolio standard, which is important, then you wouldn't have as big a jump in electricity prices as you would with 100% renewable, but yet, and you'd maintain a significant amount of cost reductions. Any next slide, please. So we talk about a no-regret strategy. This is CCS technologies are required based on a lot of people saying out there in order to reduce the amount of cost implications of CCS on the grid. The big concern with CCS right now has been the cost of CCS, and Net Power provides for a cost-effective version of CCS. The goal is that renewables can eventually get there, with renewables and batteries increasing for the next 50 years. The question is when renewables can do that. Net Power provides us for at least a bridge, if not a destination, for technology to be able to achieve a zero-carbon baseload generation. Next slide, please. In the IEA, if you look at not only central generation, but also industrial uses of carbon dioxide and industrial deployment of CCS technologies, in order to meet 2050 CO2 emissions, industrial sector must reduce by about 2/3. And projections are that in the industrial sector, energy use will increase about 44% over current levels. So we have to get a lot less energy intense as electricity use continues to rise. And really, IEA's view is that CCS is a requirement in order to achieve that. When you look at the energy density of traditional generation, it's so high for industrial generation that a lot of people are talking about central generation, the point sources of carbon dioxide, but when you start to look at the industrial sector, it even becomes more pronounced. And so the Allen cycle, we feel, Net Power really, we feel, addresses this, enables us to continue to grow electricity production in order to drive economic growth, but yet to reduce carbon significantly. Next slide, please. We do talk about EOR infrastructure because that's where we'll start. Each power plant enables us to build about a 60-mile pipeline economically. We think new gas demand over the next 20 years, about 200 gigawatts of power would support about 4,100 miles of pipeline. That's about 700 Net Power turbines. So you could build out a CCS infrastructure that stretches across the entire U.S. with that, with the EOR demand, and then then you've economically built your CCS infrastructure, which you can then put CO2 in for as long as you need to. Next slide, please. But EOR is not a local opportunity, it's a global opportunity. There's no reason that we can't use EOR as a bridge by which to reduce the carbon intensity of our liquid fuels while also building out the CCS infrastructure. You can see everywhere in the world has potential for EOR. There are pilot projects happening in Asia right now, happening in the Middle East, and happening in the commercial operations happening in Europe. So this, you could couple Allen cycle with enhanced solar recovery. You provide for a zero carbon solution, not only on the power grid, but also a decarbonization of your a reduction in carbonization of your liquid fuels, and eventually a build out of the CCS infrastructure. Next slide, please. Now, we're very encouraged by a lot of people continuing to look at technologies that utilize CO2 as an important feedstock in their processes. There are already technologies out there that do that. Methanol production is one of them, urea production is another. There's emerging technologies in cement production and liquid biofuels and hydrogen production and other areas where CO2 is an important feedstock, and we at Net Power are very interested in those technologies because they enable not only that CO2 to be sequestered, but also that CO2 to be utilized as an important feedstock in the industry, and enables additional economic production. There are current tax credits for sequestering carbon dioxide regardless of where it's used, and so we would encourage all entrepreneurs out there to come up with new CO2 uses for high pressure, high quality streams of CO2 that can then be utilized in industrial processes. So I believe that's my last slide, so I guess, Andreas, now do we open it up for questions?
So thank you, David, for those thoughts. I'm hearing echo. Maybe you can mute yourself for a second. Yeah, so just to bring in also the other people in the room, just to briefly introduce, we're also joined today by 4 ELEEP members. One is Lorenzo Grande, a current fellow, who is an analyst at ID Tech X, a British tech consulting firm where he studies the potential of energy storage in several fields. Amanda Glazer-Bly, who is a social media specialist at E.ON, one of the largest utilities in Germany. Steve Sparber, who is a legal counsel at the PJM Interconnection, and formerly at FERC, the Federal Energy Regulatory Commission. And Georg Kaspari, who is working at the International Finance Corporation, a member of the World Bank Group on clean tech operations, finance, and strategy. So just to open the floor now, broadly, if anyone wants to signal a question to me, feel free. I'm going to just kick it off with one question, which I would love for you, just from before we maybe dive into some of the broader policy topics, maybe you could give a little bit of context about how it came to the demonstration project and the decision for that site specifically. So I'd be interested in how it ended up being La Porte, Texas, what the advantages of that particular site are, and then maybe you could talk a little bit about what you mentioned, that different customers are expecting different things from the demonstration site itself. Maybe you could go a little bit into the detail of what that means.
Yeah, no problem. So a few questions there. One was why Texas and why La Porte? You know, for us, Texas was a great place where we had a lot of expertise on site in the area of constructing projects. It also enabled us to be on site next to an existing air separation unit that enabled us to lower the cost of demonstration. Because it's a open market for power generation, it enabled us to put the power on the grid in a flexible way so that we could test the unit as we needed to, and then eventually move on to wherever we wanted to take the plant. The ERCOT enables that flexibility. The other question was around what customers want to see out of the generation asset and out of the testing program. You know, people want to see demonstrations that are at scales that are relevant to their business. 50 megawatts thermal is a scale that is significant for power generation technologies, and enabling people to really look at how you're going to operate this plant in an industrial setting and in a power generation setting with real operators, real control rooms, real equipment that's on site. All the maintenance issues that you're going to see in the commercial facility, you'll be able to see in a demonstration facility. People want to see that the plant can be started up from cold, that you can have emergency situations that are safely operated, and some safety is something that we're really focused on, ensuring that this plant is operated in a safe manner. We're setting up all the procedures that you would then use for a commercial facility. So customers really want to see, these plants have to run for 30 years, and customers want to see the professionalism that's required in order for these assets to run for 30 years. And one of the things that our partners in CB&I, Toshiba, and Exelon have brought to the table is that those hundreds of years collectively of experience in the power generation business that provides the credibility for this technology to then move into commercial operation and commercial use. When a company like E.ON is not going to just trust a small company to deploy this technology to power 150,000 homes and for that power to stay on 24/7, they're going to require a level of expertise and a level of thoroughness in order to deliver that technology to their future customers. And so really seeing an integrated system down in Texas is something that customers have really wanted to see. Obviously, there's also performance implications. There's a lot of things that we're looking at as to how materials will work, what materials work, what equipment works well, how does our control system work, and all in an integrated way in a professional environment so that we can move to commercial. This for us is not a science project. We're at a scale that now it's a real demonstration facility that has to work in order to generate power. Does that answer all your questions? I'm not sure I got them all.
No, thank you. That helps a lot. I'm going to resist doing a follow-up for now. Can I take a question from anyone else? I got Steven here. I hope we can hear you.
Thank you. Can you guys hear me?
Yeah.
All right, good. All right, I got it working on my iPhone. So thank you very much, David, for the presentation. I won't hold it against you that you did the demonstration project in air condensate PJM, but
PJM is important for us going forward.
Sorry, what?
PJM is important for us going forward, for sure.
No, excellent. No, so and we definitely appreciate that. And I'm actually one of the areas I work on is our markets here, and so your talk about the the flexibility and operational aspects of the resource are really sound encouraging. My question, just actually on that note, or one of my questions is, have you guys figured out, like in terms of weather conditions? So obviously, one thing we're dealing with PJM is gas and cold weather. We had a whole redesign of our capacity market geared largely towards performance issues in the winter. Do you think your technology, rather, if it's going to suffer all in cold weather versus hot weather environments?
So the great thing about CO2 is that when it gets cold, it doesn't go solid; it goes liquid. When it's freezing outside, our performance and our efficiency actually improves remarkably. So a plant up in New England is going to perform at a much higher efficiency than a plant down on the Gulf Coast of Texas. And so if it's cold outside, our plant is performing at its peak efficiency. You got to worry about heat tracing on your water cooling lines, because if you have water cooling, you still have to heat trace those lines. And so you design to whatever temperature you need to in order to do that. If you're going air cooling, which is, I've been a lot of plants down in Boston, and they've got huge air-cooled condensers because it's cold most of the year. So if you have air-cooled condensers, you really don't have any water or any ice formation that you'd have to worry about. CO2 for us, as I say, it's colder the better for our facilities. It's actually, as you get hotter, as you get more humid, that's where you have to be a little bit more careful. But in the winter, where power demand is really high in the Northeast, and where you don't always have dispatchable power or non-dispatchable power and renewables available, you need that baseload generation that's there and reliable. Our facility will be operating.
Okay, that's great to know. Have you guys been, just a quick follow-up question, have you guys been in touch with anyone at PJM about your technology? Exelon was one of our members. We work with a lot, but I don't know if you guys have had a chance to talk to any of our engineering folks.
I personally have not. Doesn't mean that other people involved with the project have not. I know that, as you say, Exelon has a lot of generation in PJM, and I'm sure they've been in contact with them. But I personally am not happy. Would love to make that presentation if you'd like to set it up for us. Okay.
Yeah, and I'll get in. I'll talk to a few folks internally, just in our we have an emerging markets team that deals with all the incoming stuff, and we always like to keep abreast of what's going on in the industry. So I'll definitely tell them about this. Thank you.
Yeah, thank you.
Yeah. So I'm looking here at the other two participants. Do you have a question, Amanda?
Hello. Yeah, so I have two questions. I think one is maybe the big obvious question. You're only doing this for natural gas, and the question is, how much of a step further is it to do it for coal? Because I think the logical question, that's where it's needed. So I guess that's maybe the big obvious question. And then the second question is, you're comparing yourself a lot to the combined cycle generation, and how much of the heat, are you using 100% of the heat that you're producing? Would there be any sort of potential to say, okay, we use less of the heat, or we don't need all the heat, and there's some sort of way to make it also into a combined cycle plant as well as a CCS plant?
Yeah, so on the first question on movement to coal, so ARURS continues to look at the coal implications of the technology. We right now we've been supported in the past by the Department of Energy and Climate Change out of the UK for the path to coal work, as well as the Lignite Energy Council in the US and EERC up in North Dakota, as well as some of the utilities up there like Basin Electric and ELEEP. And so we continue to look at how this technology will be applied to coal. We just actually gave a paper at ASME Turbo Expo on the technology's application for us. it is a step that comes with, with coal. You have obviously additional risks and things that you have to think about that are in coal that you other emissions that don't exist in natural gas, other constituents that don't exist in natural gas, and so you have to deal with them so that you can maintain your technology as a zero emissions product. We feel like we do have some really interesting applications there. We're utilizing, there's been a lot of development in gasifier technology as a result of China's use in gasification for chemical production, and so we can really use a very simple gasifier with an input of the coal syngas into the alum cycle. So the core alum cycle doesn't change when you move to coal technologies or syngas derived fuels. And so what you really need to think about is how you deal with the upstream coal and the ash going into the alum cycle, and that's where we've spent a lot of time now looking at that. So when we look at a coal system, we're looking at efficiencies of about 47%, including carbon capture, and that's with commercially available gasifiers today. And when you look at lignite, which is, I know in Germany is something that you guys use a lot of, there's only about a 2 or 3% reduction in efficiency. So you're in the mid-40s with full carbon capture for coal. And efficiency isn't everything. Cost is obviously very important. Because we're utilizing commercially available gasifiers, our footprint's really small, and because we don't have a big steam system, we feel like we're going to be directly competitive with existing coal assets that don't capture carbon. So your supercritical coal plants, you would never build that again if the alum cycle coal version was available. So yeah, we very much are interested in coal applications. As you say, that's where CCS is a huge application, and if you like this technology on gas, you'll love it on coal. In the U.S., our political environment, coal isn't as important for us, but if you look at the growth of coal in places like India, China, Indonesia, even across Europe, there's terawatts of coal power that's going up. That we would like that technology to be zero carbon as much as possible, no air emissions, and the alum cycle coal technology enables for that. And if you want to do another one of these, I can go into that technology in more detail. Your second question was around combined heat and power. So our basic design is that, yeah, we produce two product streams. We produce electricity and CO2. There are designs that we've looked at for production of steam alongside with electricity and CO2. Your efficiency obviously goes down for power generation, but your total heat duty obviously goes up. So yeah, we've looked at combined heat and power. It's not a core focus of us. It's not something we're going to be testing out in the demonstration plant, but there are customers who are interested in CHP projects, and we're happy to talk about that.
Okay. So I'm now looking at Lorenzo to take on the next question.
Yes, so I have a question regarding your partnership with Toshiba. So how did you choose this company, and how did you approach them? Why do you think they were the best for your pilot project?
So Toshiba, Toshiba for us has been a phenomenal partner. They've been in since 2011, and we have support all across the organization. I've been very impressed with them as a partner. Really, for us, we needed somebody that had both gas and steam turbine technology and expertise. They're one of the leaders in the world in steam turbine technology. They push steam temperatures up to places that other people haven't, and they've got a lot of operational expertise that they were able to bring to the table. Gas turbine technology, they're a licensee of GE in the East, and so they maintain a lot of products in Japan and in Asia for other people's products. That, personally, I think Net Power is a way for them to look at the gas turbine market in an interesting way and to develop a unique product offering for the market. So how did we approach them? We made, I think, like anything, it's a relationship business, and so we made some relationships at Toshiba. They saw across the organization a strategic interest in where this technology could take their business, and they slowly got into the technology, and we built out a relationship over several years. And as I said, they're an incredible partner for us, and we look forward to deploying a lot of Toshiba turbines all across the world. Does that answer your question?
Yes, thank you.
So if I may take a question as somewhat of a follow-up there, I was wondering, you did mention receiving a grant from DEC in the UK. At an earlier stage, I also read the announcement from 2012 on your website. Are you looking at all towards Europe, either for marketing the product in the long term, or for receiving further policy support to demonstrate the project, or in other ways benefit the technology?
Yeah, I think our goal now is to build commercial facilities and to continue to demonstrate it at a commercial scale. And Europe is obviously a leader in decarbonization and a view towards the necessity of doing something about climate change, and that's an important piece of our story. So, and in the North Sea, you've got a huge application for enhanced oil recovery, and that Norway has been doing for several, Statoil and Norway have been doing for several years now, for tens of years now. So there's a lot of experience there, a lot of expertise. So yeah, we're very much interested in European countries in order to deploy the technology, both in gas and in coal versions of the technology.
Andreas, can I ask you a quick follow-up question?
Oh, of course, yes. Please, Georg.
Yeah, I currently work a lot on the startup space in this area, and I was wondering about your financing structure so far and looking forward. I don't know how much you can say about that. I hear that so far you're partly financed from DEC. What is other backing that you have so far? What's further financial backing that you're looking at to in the future? I'm presuming that DEC is some sort of grant, but what other financing mechanisms are you looking for, especially with respect to an expansion overseas? Thank you.
Yeah, so we have been lucky enough to receive grants from several different entities now. We have raised over 140 million from CB&I and Exelon. They saw this as a strategic investment in the technology and in where this technology could go. So that's predominantly how we've been financed. Eight Rivers has also invested significant amount of capital in the technology's early stages and continues to support the project going forward. So we also, our supplier network is something that we continue to build out, and a lot of our suppliers see strategic value in where this technology will go. And there's been a lot of interest now from the financial community in what this technology can become. And so a view towards continued investments. We're going to need a lot of investments, both by utilities in net power plants and by IPPs or independent power producers in power plants. And net power for us is we're going to license technology to anybody who wants to build it. We're not going to build the technology. We're not going to build terawatts of power all ourselves. That would be impractical and really expensive. So we're looking at a lot of different financing sources for not only the first commercial facility, but ongoing commercial facilities as well.
Okay, thanks.
So can I take an immediate follow-up question from anyone else? Otherwise, no? Well, I have a question here broadly around how you framed the company going forward, initially without too much policy support. And you just highlighted the fact that one reason why La Porte was a good location for the demonstration project was kind of open access to the market, the wholesale market, and kind of a less policy-driven context. What other kind of framework conditions, though, do you still need for this to be a success, even in the immediate term? Are you mainly looking at EOR type projects in the immediate term? I mean, you indicated that might be the case initially. Or are you seeing potentially projects with larger pipelines without EOR in the near future?
So yeah, for us, a policy incentive to build a first commercial plant would be fantastic. We would love if a government or a large entity would provide support on a non-technology specific or a technology specific basis for us to build a first commercial facility. It's not something that we spend a ton of time on because we really do see an opportunity in enhanced oil recovery projects and being able to tie into existing enhanced oil recovery projects for our first couple commercial assets. But policy support for new technologies, building that first commercial plant is something that's going to be a big lift. And if either a PUC or a large utility or a government was able to support some of that, we would very much appreciate it.
And in addition to that, once those first couple commercial plants are deployed and people realize that there's access to low-cost, clean CO2, a lot of the processes that have been developed by various startups will become economically viable. The reason they're currently not deployed at large scale and economically viable is because you need a cleanup process in between the flue gas of any power plant and that CO2 conversion utilization facility. One great example is a company, Novomer, that takes CO2, converts it to polymers, and just partnered with Ford. Their process actually requires CO2 at the exact temperature that we can provide, and we can provide it at the purity which their system can utilize. And that's a huge opportunity when you start to think about every seat cushion and dashboard in every vehicle essentially being produced from the CO2 produced from a net power plant. So I think the opportunities are vast for CO2 utilization, and I think net power actually enables all of those CO2 conversion utilization strategies to actually start to happen as we provide an economic source of CO2.
Thank you. I'm not seeing any raised hands at the moment. Oh, no. If I may, then still another question. I'm still interested in you focused again on the competitive advantage in certain regulatory spaces where potentially air pollution is something, or high air pollution standards might give you a leg up in siting a plant in that jurisdiction, or a water scarcity. Which of these environmental constraints do you think will play the bigger role in driving kind of initial adoption, if at all?
So I think it depends on where you are. I think different customers are going to have different requirements. Certain parts of the U.S. are of the view that really what they like most about net power is the security that, as we call it, the no regret situation, where if I build a facility tomorrow, that 5 years from now, new regulation is not going to come down that's then going to hurt me and make that plant uneconomic or unable to run. And so that decision where people 5 years ago, 7 years ago, built a brand new coal plant in the U.S. that are now slated for retirement. So for the utility and for its ratepayers, that's not a great situation. So that security of supply and security of future operation is something that I think people value a lot. In other regulatory environments, CO2 tax is available today. There's cap and trading going on in California, cap and trade going on in Europe, cap and trade going on in China, starting in 2017. And so, the ability to produce 800,000 tons of credits a year from a single unit, if you're at $7 to $10, that's $6 to $10 million a year of additional value that you're able to generate from your asset, which is non-trivial on a facility. So that's going to help, I think, in other areas. As I mentioned, the non-attainment zones around major cities. You're looking at what's happening in Asia right now with some of the air pollution problems that they have around some of their major metropolitan areas, both from PM issues, NOx, SOx, all the issues that we used to deal with here in the U.S., and we implemented all the air quality controls in order to reduce those. CO2 is part of that equation now, and so if you can go in and offer something that doesn't produce any NOx, any SOx, any CO, and no PM, obviously, because of natural gas. And when we move to coal, no PM there is either. Then you're able to either have the option for future CO2 removal or actually do the CO2 sequestration directly. I think it's a great value proposition for people. So I think your question is right, that regulatory will drive, but like energy, energy is so complex and so local, depending on what goes on in policy and economics and natural resources and technology, in local water environments, local air quality issues. A lot of stuff has to think about when you're siting a new power plant, when you're building a new power plant. Something as a utility, I don't envy that position. You're making 30 years decision for people, and that plant again has to operate, because if the lights go out, people get very upset very quickly. And so the reliability, the flexibility, all those abilities that are required in the power industry, that's very important for people. So it's something that why we've focused so much on our strategic partners, because they provided us a lot of that support and a lot of that credibility for the market.
There's, I think, one last point I would love to touch on, which is one additional barrier to CCS development that is often pointed to is more public resistance to projects. And of course, the specifics of each project are different, but is there something different about your project compared to some of the barriers to development in other contexts that give your project a leg up in preventing kind of the local community and maybe local forces from resisting the project?
So there's a lot of things to love about net power. Right? It's a small footprint. It can utilize zero water. It actually produces water for its own cooling if it needs to. Doesn't commit. If you sequester carbon, doesn't contribute to CO2 emissions. It doesn't have NOx issues. So with any big power station, with any industrial development, you're going to have NIMBY concerns. You're going to have development concerns wherever you are. I think if you're realistic about where the energy grid has to go in the next 25 to 50 years, renewables, what we see right now, and what a lot of utilities communicate to us, is that renewables by themselves aren't going to get us there. We need to produce something that's dispatchable, that can be there when it's cold in the Northeast or when it's really hot in the Gulf Coast of Texas. And there's nothing like fossil fuels that do that, with the exception of, and if you can do those fossil fuels with sequestration, then your climate change issues really reduce significantly. So there's a lot of stuff to love here on both sides of the aisle in the U.S., as we say. You get a decarbonization of your liquid fuels, increased domestic or local oil production, and on the other side it is decarbonization of the grid in a way that doesn't jeopardize reliability or increase economics.
Well, thank you, David. Thank you, Damien, for taking your time to meet with us today. The hour is up, but I think it was an interesting presentation for all of us, and it's an exciting project, I think, for the potential it has. So thank you very much for taking your time to present the project to us, and thank you to the ELEEP members for joining in for the conversation. Also, before ending, I'd like to thank the sponsors that make ELEEP and these virtual discussions possible. It includes the European Union, Robert Bosch Foundation, and the Alliance Foundation for North America. And with that, I'd like to close this session. If you want to find out more about ELEEP, visit our website, www.eleep.eu, or find us on Facebook, Twitter, or YouTube.
And if you want to find out more about NetPower, netpower.com as well. Sorry, Chris.
And thank you for that pitch as well. And we'll put the link up on the video as well. So thank you, and goodbye.
Thank you all.